Welcome to Math 31. This is a continuation of the lesson on limits of trigonometric functions. Just going to go through a few more examples, 10 or so of them, showing just some different looks. These can be tricky problems, but the method is always the same. You substitute in to take the limit. And in this case that makes good sense because as you take the limit, we can see that we have no denominator. This is not going to turn into a 0 over 0 expression. So when we replace the x with pi, we get pi plus pi over 3. Now, some of you are thinking, well, why not do the a plus b formula on this one? And of course, you could do that, but it isn't really necessary because in this case, you could just add them together. Pi plus pi over 3 is equal to the sine of 4 pi over 3. Get a common denominator and add them. So 3 over 3 pi plus 1 over 3. And then this becomes an exact value problem. The sine of 4 pi over 3, that's going to be in quadrant 3. And the sine of pi over 3 is root 3 over 2. And of course, because you're in quadrant 3, it's going to be negative. So we end up with this. So always be aware of that. Start off by doing the substitution thing and then see where it takes you. Now, number 9 looks a little bit more complicated, and when you start seeing things like cosecant and cotangents, you're probably thinking correctly that you need to do some work with identities, and that typically is the case. You need to remember that we really don't have many things to work with, many tools. We've got the sine theta over theta formula. We've got 1 minus cos theta over theta. And the last lesson we did tan theta over theta. So there's really just 3 things to work with. So if it's not of that form, then we have to be prepared to play around with it a little bit. And when I look at this, first off with substitution, cosecant of 2 theta is the cosecant of 2x would be cosecant of 0 over cotangent of 0. Now, in working that out, the cosecant of 0 is a problem because this is equal to 1 over sine of 0. So that's going to be 1 over 0. And that's undefined. Now that doesn't mean that there's no value for this one. It just means we cannot simplify it further that way. So we have to do our best to simplify it until we get into a form where we get it into the 0 over 0. So when I look at cosecant over 2x, I'm thinking 1 over sine 2x. And as always with these, pause me and go through it on your own. Many of these are just algebra. There's not a lot of new material, new things happening. So 1 over cos x, or 1 over sine 2x, all over cos x over sine x. Then this becomes, as we invert and multiply, we'll get 1 over sine 2x multiplied by sine x over cos x. So far, so good. We're going to have to do a double angle on this one. So this becomes 1 over 2 sine x cos x multiplied by sine x over cos x. And we get what we wanted. The sine x go away on us. And then when we evaluate this, we'll get, or as we first off write it out, we have 1 over 2 cos squared x. We're okay because when we replace x with 0, we get 1 over 2 times 1 squared because the cos of 0 is equal to 1. So this is equal to 1 over 2. Now, number 10, not a difficult question, but it does have a look to it that can throw you off, namely the fact that this one is squared. And you can get around that problem by using limit properties that we occasionally run into. Now, this is actually equal to the sine of 2x over x, and then all this squared. That's the nature of limits. Now it doesn't matter if you write it like that, but the key idea is that you take the limit of sine 2x over x, get an answer, and then multiply it by itself, and then you'll be fine. So I'm going to work out the inner the way that we were doing them in the previous lesson, which is I'm going to set this one up, break it up, and then work this one out. Because I got an x down there. What I want to introduce is a 2. So I really don't have to break this one up too much. I bring in a 2 there, but then I have to bring in a 2 up top. All this being squared. And then as I take the limit, that's going to be 2 times 1 all squared. So 2 squared is equal to 4. And this is our answer. Moving along to number 11. Now we have a few interesting choices with this one. Because that tan theta over theta, or tan x over x, is equal to 1, we did see that in example number 7. That is not on your formula sheet, so you either remember it or you ignore it and don't deal with it, because you can always solve these ones in terms of sine and cos. But let's take this one and use what we have. And I'm going to use the fact that the tan of x over x is equal to 1 as x approaches 0. So this would break up into a factor of 1/3 at 3 on the bottom, and then we have a tan 2x on top. And now we could take the x separate if we wanted, but you might remember that it's easier because we're going to need that x. We might as well keep it where it is. And then all we need to do is introduce a factor of 2, and that this is going to be equal to 1 when we take the limit. Of course, because we introduce a factor of 2 on the denominator, we have to introduce 1 on top. So we end up with 1/3 times 1 times 2, which is equal to 2/3. So that's probably the easiest way to work with it. Otherwise, you'd have had to take that tan 2x and express it in terms of sine over cos. Solvable, but a lot of extra hassle involved. Now, number 12, another square one. Now, this is a good one for you to pause and go through it on your own. Actually, isn't that bad of a problem. We recognize that this whole thing is, in fact, the sine of 3x over the sine of 4x. Then this is all squared. Break it up in the middle. So this is the limit of x approaches 0. And by the way, this is 0 over 0. I kind of whistled past that one, but we should check. But the sine of 0 is 0. Sine of 0 on the denominator also 0. So now we take this one, and sine 3x on top, and then we have the sine 4x on the bottom. We introduce a 3x there. We introduce a 4x there, and then we are aware that we have to balance it with a 3x on top and a 4x on the bottom, and all this is squared. So we end up with 1 when we take the limit times 1 times 3 over 4 all squared. So 3/4 squared is 9 over 16. Now, one thing that you might, at this point, if you're comfortable with these, you might eliminate some of the steps. So at this point, when you have the sine of 3x over the sine of 4x, if you follow the pattern of what we've been doing, you'll see that when we introduce a 3x in the bottom, to work with the sine 3x on top, to balance it, we're always putting a 3x there. And the same thing with the sine 4x, because we put one on top, the balance factor would be the one on the denominator. So some people just go directly to that, and then they say 3/4 times 1 is equal to 3/4, and of course this has to be squared. But That's an option. So the balancing act, as long as you recognize the pattern of it, you can go directly to that and you'll be fine with it. You're not going to get extra marks for doing the extra work with it. I'm showing the more conservative, safe way to do it. But many people, after they've done a few, they start to figure, well, I don't need to do this exactly. And as long as you do it right and you're careful, no problem. It always comes down to that, though. You can get away with all sorts of things as long as you don't make mistakes with it. Now, this is another one. I'm not sure why I put this one in here, because it actually doesn't break a lot of new ground. But if you do want to take this sine of x plus cos x, as we're not approaching a zero number now, and because we don't have a denominator, the expectation is that it's going to be a numeric value. When we take the limit, the sine of pi plus the cosine of pi gives us 0 plus negative 1. So it's equal to negative 1. But just a reminder that you have to occasionally deal with those sorts of things. The next one, I think, will push you a little bit more. Now, if you do plug in pi over 4 to this, to substitute it, you get the cosine of 2 pi over 4, which is pi over 2, over top of cosine pi over 4 minus the sine of pi over 4. And this is cos of pi over 2, and top is 0. And then cos of pi over 4 is 1 over root 2 minus 1 over root 2, so also 0. So it means we can go further with it. And the only real thing we can do with this, as far as I can tell, is that numerator, cos 2x. And then we have to deal with, well, which version of the identity do we want to use? And because I'm looking ahead and I see, well, cos x minus sine x, so I'm thinking that if we take that numerator, the double angle, and break it into cos squared x minus sine squared x, we've got a good chance at factoring that one down and then getting a cancellation. So in fact, this is exactly what we can do. We get cos x plus sine x, it's a difference of squares, minus cos x minus, or times cos x minus sine x, and then this is all over top of cos x minus sine x. And then the limit as x approaches pi over 4. These divide out, so we end up with the limit as x approaches pi over 4 of cos x plus sine x. We take the limit and we get the cos of pi over 4 is root 2 over 2, and then the sine of the same is root 2 over 2. And then when you add the two together, you'll get 2 root 2 over 2, which is just equal to square root 2. So this is why you get good at identities, so that you can make these simplifications. And number 15, this is an interesting problem, sort of, because it looks like you're going to have more to do with it than you really are. But this is also a substitution one. When you plug in 3 pi over 2 on top, and then 2 times 3 pi over 2 on the bottom, well, the cosine of 3 pi over 2, or 270 degrees, is 0. But the problem, or the good thing is, on the denominator, it's just 3 pi, so we can handle that. 0 on top will give us a limit of 0. So reminder, substitute in. Now, tan x over tan 2x is an interesting one because, again, we're dealing with the issue of whether we want to use the tan simplification formula or not. Now, if you do not, you're going to have to do a bit of work again with this in terms of sine and cos. But I'm going to actually do it both ways just for the fun of it. It does give us 0 over 0. You can check that out, but the tan of 0 over the tan of 0 would be 0 over 0. So if we really wanted to do the long method on this, we would take that tan x and write that as sine x over cos x, and then at the same time sine 2x over cosine 2x. Now, of course, we cannot cancel those because the argument is different for both of them. And then, if we cleaned up this one by turning this complex fraction into a single fraction through division, it'd be sine x over cos x multiplied by cos 2x over sine 2x. Now, if we break it up now, the way that we have been doing it in the past, we can get it in a form we want. Because this is going to be sine x, give some space for that one, and times a sine 2x on the bottom. Now I'm changing the order a little bit, and then I'm going to keep this as cos 2x and cos x. Now you could have broken them up as well, but I didn't bother because the only formula we have for cosine is 1 minus cosine, or cosine minus 1. So I'm going to keep them off to the side and just deal with the signs. And all I need to do now is introduce an x on the bottom to make this one go away, and then a 2x on top. Now, of course, in doing that, I need to balance it off by introducing an x on top and then a 2x on the bottom. And then when all is said and done, this is 1, this is 1, and then the cosine of 2x is the cosine of 0 over the cosine of 0. Now the cosine of 0, remember, is 1. So this turns into 1, and then the x's cancel, and we're left with 1/2. So this whole thing is equal to 1/2. But that's quite a bit of work. So if you use the faster method for tan, you would have gotten this. You break it up right away, so tan x and then tan 2x. Introduce an x on the bottom to make that one equal to 1 when you take the limit. Introduce a 2x there to make that equal to 1. And then the balancing would be an x on top and then a 2x on the bottom, and that is 1/2. So we also get 1/2, much quicker. So the choice is yours. Just remember that you don't have that in your formula sheet. Now the special cases are called this because they force us to use more sophisticated methods to simplify. Now you know, I think, that the idea is to substitute in. And if you substitute it in this case, we're going to get 0 over 0. Now notice we're not approaching 0. We're approaching a non-zero note. We're approaching a non-zero number. And the problem with that is that we don't have a rule for it. Those sine and the cos and even the tan are always as x approaches 0. So if substitution doesn't work and there's no other obvious simplification, we're in trouble. So this is really our last-ditch approach. Substitution didn't work, neither did regular simplification. So what we have to do is a different type of substitution. We pick a variable that is harmless, say theta, and make it equal to what we have here for the limit. Now, to make it a little easier to see, if you bring this pi over, it can be written like this. And you see now we have it approaching 0. So let theta be equal to x minus pi. And now we have that much of it set up because theta is approaching 0. So now we can use those formulas that we have. The problem is we have to deal with this x and the x minus pi and express them in terms of theta. But that's not an issue because we take the x isolated and we get theta plus pi. So in fact, sine x becomes the sine of theta plus pi. And then the denominator is x minus pi, which is in fact just equal to theta, according to the original substitution that we have. Now that still isn't perfect, but if you use a sum difference formula on it, so use sine A plus B, that would be fine. But actually, better than that, if you take a look at your formula sheet, you don't even need to use a sum difference because that one is given to us. Conveniently, sine, this is a cofunction identity, and the sine of theta plus pi is equal to negative sine theta. So negative sine theta over theta. And that's the limit as theta approaches 0. And then that's good, because when we take the limit, we have a negative, but that's negative 1, because sine theta over theta is negative 1. So therefore, this limit is equal to negative 1. So not quite as straightforward as the other ones. And the tip-off with these is when nothing else works, when it's 0 over 0, and when you're approaching a non-zero number. So special cases, make that little note, this isn't too clean, but when approaching a non-zero number. And I won't write this one down, but nothing else works. No other simplification will make the problem go away. Take a look at another one. I think this is the last one that I've got for you guys. And we run into the same problem. We substitute in pi, and we do get 0 over 0, because negative 1 plus 1 on top is 0. Sine of pi is also 0. We are approaching a non-zero number. Not much we can do. So we bring that pi over, so it is approaching 0. And then we try to get this thing set up in terms of an outside variable. So I'm going to let theta be equal to x minus pi. And that would mean that x is equal to theta plus pi. So this expression now is going to be theta approaches 0, and then cos x becomes cos of theta plus pi plus 1, and sine x on the bottom becomes sine x becomes also theta plus pi. Okay, no cause for concern there. Now, keeping going with this one, we see we have two identity, or the use of two identities for this one and this one. So we replace the sine theta plus pi with negative sine theta. Okay, and then in the numerator, cosine of theta plus pi is equal to negative cos theta. So this still doesn't look like it's a good situation, but it's a better situation. Now if we rewrote that one, just to make it a little easier to analyze, we could go 1 minus cos theta on top and negative sine theta on the bottom. And the reason that is helpful is because the setup now it shows that we can take that 1 minus cos theta and we break it up the expression and the negative sine theta down below. Now the negative sine theta, you can either keep the negative there or just keep it outside, or you can bring it outside the entire limit, because that would work. But anyways, we can just keeping it there as a negative 1 is going to be fine. We introduce a theta on the bottom to make this one equal to 0, and then a theta on top for the sine theta to make it equal to positive 1. And it's not going to make any difference, though, because when we work this one out, we get 0 times negative 1, so that still is equal to 0. So this, in fact, is equal to 0. All that work just took us this far. So that's how these go. That's going to take care of the limits. The next lesson we'll be looking at derivatives of trig functions. So thank you for your time.